Yeah? Okay. So I thought since one of the themes for today is dynamics, I'll just give kind of an overview of a lot of the dynamic connectivity work that we've been doing in the lab. And at the end, so I'll cover, most of these topics, I think. Starting from different approaches that can be used, different ways to combine the data. And then at the end, I'll talk a little bit about some open questions, because there is a fair amount of work that's been done, but there's also a lot of open questions. And so hopefully that'll stimulate some ideas for a project for Brainhack. With obviously the brain, we're collecting fMRI data from the brain, and I'm going to primarily focus on resting data during the talk. And so we get these time series from the data, and until, I don't know, 5 years ago or whatever, the huge majority of studies focused on computing functional connectivity at the average, averaged across all of that, all of those runs. As we know, though, the brain is highly dynamic, and especially when you're resting in the scanner, it's unconstrained, and you're doing a lot of things that we can't control experimentally. And so a much more natural way to analyze that is to think about the connectivity of the brain sort of dynamically changing over time. This is consistent with what we observe behaviorally, and we essentially want to exploit that in the brain activity and really leverage the data. In terms of existing approaches that are out there, this isn't completely comprehensive, but you can focus on voxels or regions. You can focus on components or networks and look at sort of their interrelationship. You can use like windowing to compute connectivity over time using a windowed approach, or you could do a more general sort of a time frequency decomposition and sort of adaptively fit to the data. There are other approaches that Maziar will talk about next. Then if your focus is on really trying to estimate, is the brain getting into a certain pattern of connectivity, which we could call states, or brain states, there are lots of ways to do that. Obviously you can do clustering, or you can do PCA or ICA, etc. And then at the end, we have to figure out how to make some inferences about that. And that could include talking about individual states. Do they have a particular dwell time? Do they stay within a, are they kind of sticky? Do they, once you get into them, you tend to stay longer. Or you could do sort of a multi-state summary. I'm going to need a new battery here. My battery's dying. Or a multi-state summary where you, huh? It's controlled by my laptop, so I want to use this one. So. I stole these batteries from another, for something else that I think my mouse that was turning into. All right, okay. And then you can do, the summaries across all of the states, really kind of a global measure. One example is called a MedEstate. I'll get into these details as we go along. So let's first talk about some of the windowed approaches. The one that was introduced by Elena Allen, actually we have been using this approach I think since 2010 or so. Essentially taking the resting fMRI data and decomposing it into independent components, spatially independent components, each one of which has a time course. And then instead of taking the covariance or the correlation, cross-correlation of all those time courses, we can use a windowed average and compute a time series, basically compute that covariance matrix at a single window and then shift it and compute it again. So we get a time series of these matrices. That's obviously a lot of data. Here's an example of some of the changes that we see in real data in a given subject. The basic idea is, of course, that instead of characterizing this kind of pattern as a correlation of 0.4, it's much more informative to say these were correlated at 0.8 at the beginning, and then they're essentially not correlated at the end. Okay, that's the kind of information we want to capture. And so at the next step, we can do clustering of these down into centroids of states. You can do this a lot of different ways. So here we have 5 states, and then once you do that, you can estimate which state a subject is most similar to at each point in time. So this subject went from state 3 to state 2, then up to state 4, etc. Okay, so there's a lot of information here, and there's a lot of ways to really try to estimate these things. I'll just show a bunch of examples from studies that we've done already. This is some of Insula Domain's work, where we basically took a large schizophrenia data set. These are the independent components, and they're grouped into domains. So here, for example, are the components that are most similar to the default mode network. Here is visual, etc. Down here is the cross-correlation between the time courses in all these components, ordered along domain. And so you can see here for healthy controls, this block here is the visual and motor regions, so sensory motor block here. You see that there's a lot of strong connectivity within that domain. Over here we have default mode, and it's a little hard to see, but there's weak negative correlation of the default mode network with these other networks here. This is schizophrenia, and this is the difference. And you can see this is a static approach. We're kind of assuming an average, looking at the average, and you get a pretty strong effect. So not to say that the average approach isn't useful, but I'll come back to this later and show that we can do more in a dynamic approach. Right here, for example, if we take that same data, the same decomposition, and cluster it, you compute the window correlations and then do clustering, we get 5 different states here for healthy controls and for schizophrenia patients, and then here's the difference. And one thing to note is that the differences are kind of concentrated in particular, certain differences are concentrated in different states. Okay, so the pattern of change is kind of unpacked a little bit more. And secondly, we can do things like estimate how much time patients and controls spend in each of those 5 states. And here we can see pretty clearly significantly more time. Healthy controls kind of hang out in these first 2 states, which have a lot of strong modularity, especially in the sensory motor block here. Whereas the patients spend significantly more time in these much more weakly connected states. There's still a little bit of modularity, but it's much weaker. Okay, and that just sort of kind of shows you how you can unpack that a little bit. And we've looked at this in multiple patient groups. So here is an example from Barnley Rashid looking at bipolar and schizophrenia subjects. And you can see if we look at sort of the lines, so the colors along the circle are the domains, or the components grouped into these domains. And then the lines tell you where we get significant differences between patient groups and control groups and between the 2 patient groups. The first thing you'll notice is that most of the changes are concentrated here in state 3, with the exception of a couple of the smaller differences that are primarily between healthy controls and bipolars, who are much more similar in their brain activity than are the schizophrenia patients. And this is another example of one of the many ways you can visualize this. Instead of showing it as a matrix, you can take the modules from that matrix, and since each component pair represents 2 different components which have spatial regions, we can render that and basically get a better idea of what the spatial information in the states is showing us. And then Barnley went further and did classification, so this is looking at a comparison of a static approach with a dynamic approach, the 2 approaches that I had mentioned before. And essentially when we did that, we found that with this 3-group comparison, so chance is 33%, we get a 60% classification accuracy on a static approach, but dynamic does much better. In this case, it did 84%, and slightly higher if we actually do both, combine those together. Then this is some work from Victor Vergara looking at substance use data. So this is about 500 subjects that have various substances that they're taking, from alcohol to nicotine to marijuana. And we essentially did a dynamic connectivity analysis of by looking at comparing the subjects that are taking one or combinations of those substances. And again, we found that the changes tended to be concentrated in a small number of states, whereas the remainder of the states tended to look more similar between the groups. You can think of it as almost like a, it's also sort of helping to denoise a little bit, sort of pulling things out into separate groups. And then if we kind of look a little bit more in detail at these two states, for example, you can see here the dwell time that occurs. For example, smokers and smokers and marijuana tend to spend the most time over here, whereas controls spend more time over here. You can see some of the cells here and these are the states and these are the different groups that we've divided. And if it's highlighted, it was a significant difference. And I think this is one more example to show from Barnley Rashid, and this is from the GenR data set in collaboration with Tanya White, looking at typical development in children. So we have 800 subjects here, aged 6 to 10. And a couple things to note. These are our four states that were estimated. And what we found was that there was an age effect where the older you tended to shift from this sort of more disconnected or weakly connected state into this more strongly or modularized state. Interestingly, when we also looked at the social responsiveness scale, which is a measure of sort of autistic tendency, these are typical kids, but it gives us sort of a measure of that tendency. And we see that those kids, despite being older, tended to stay more in this disconnected state. So again, it gives you this kind of information that you don't have access to if you're looking at the average. Now, there have been some discussions about, well, is this real? Are we actually capturing a real effect here? Is it just noise in the data, et cetera? So there's been a number of studies to try to validate this, one of which uses concurrent EEG data. And this is data from Enzo Tagliazucci, where we're looking at EEG and resting fMRI, and then we have sleep staging on this data. And what we found was we estimated the fMRI states and we compared them to the sleep state that they were in. And we found, for example, that the awake condition was most strongly associated with state 1, whereas this state here was much more strongly associated with the deepest stage, sleep stage N3. And here's an example of the hypnogram from the EEG data, so the sleep stage information, and the state is here. And compared with the dynamic connectivity state, you can see there's actually a pretty tight match there. So it's already been shown by a number of groups that drowsiness is one factor in resting fMRI data, and that's actually borne out here, and it's actually, we're seeing shifts between different states as a function of drowsiness. And this is some data collected at the Mind Research Network by Lei Wu, and we are comparing here just a very large data set of about 600 subjects, very robust result, with a smaller data set of about 23 subjects that had EEG concurrently collected. And just to kind of show that we can get similar patterns in the static FNC. And then if we look at the dynamic result, we see this very interesting trend if we order them from left to right in terms of indicators of drowsiness based on the EEG delta theta power and alpha power. And we see that in the least drowsy state, there tended to be more of this anti-correlation here effect with a shift towards more of a hyper-connected state in the least drowsy condition. This is some work from Javier Gonzalez Castillo and Peter Benedetti's group, where they basically started to look at the impact of task on sort of transient connectivity. And so they have these blocks of rest, memorization, video, or doing math, sort of back to back to back, and showed that you could get near perfect predictive accuracy by using the patterns of connectivity in order to identify which of those blocks they were in. And if we analyze that data with the same dynamic ICA approach that I mentioned before, we get 5 states here, but we find that the task effect is actually a pretty strong effect. So we see, that it almost almost perfectly, again, segregates into the different blocks when doing this. And on top of this, though, we have some interesting patterns, say, within each block as well that we're looking at now. But again, task is sort of a big driver of this, but it's not the only driver. And then last, in terms of validation, this is a study by Anissa Brule looking at a large amount of resting fMRI data collected here at the Mind Research Network. So we have 7,500 subjects, and they were split into 28 different groups of 250 subjects each. And they were completely independently analyzed of one another. And when we did that, we estimated states from this, and we estimated dwell time. And then we compared the states across these independent data sets, and we found that they were highly correlated. So we basically see that the patterns that we see coming out tended to be highly correlated at a level about 0.8. And interestingly, we also find that the dwell time was pretty replicable across these. So the state that they tended to spend the most time in was consistent, fairly consistent across these 28 different data sets, again correlated around 0.8. And here's an example of 7 of those 28 groups, just to kind of give you a visual picture of it. And you can see that they're pretty similar. They're ordered sort of by similarity, with the exception of state 5, which tends to sort of flip back and forth between 2 different patterns. Okay. And here's an example of one of the clusters. And you can see that the clusters are fairly close together, but if we look across these 28 data sets, we see highly replicable patterns, and they are separated from one another quite well, independently across those different data sets. And then finally, global characterization. Instead of just picking a single state and saying this is the dwell time of that state, we can think about a state space. So here we have state 1 versus state 2, and we can think of a subject as a function of time as sort of moving around in that state space. And so once we do that, we can basically map a coordinate onto each point in time. And so characterize that as a vector here, where this is state 1 and state 2, and the number tells you which coordinate they're in for each of those states. And so we call these vectors metastates. And once we get these vectors, we can then compute lots of interesting summary measures across the metastates. For example, the total distance traveled in that space. In case this one it would be high, this would be low. Right? We also looked at, one of the nice things about the metastate analysis is, depending on how you cluster your states, you will get different results based on what type of clustering you use because of the different assumptions. So PCA will look very different from ICA, and that's expected. Whereas if we summarize in this metastate space, we get, at least in this example, we looked at an effect of schizophrenia versus healthy controls, and we found for 4 different measures, number of states, number of changes, the L2 span, the total distance traveled, we got the same directionality, regardless of whether we use temporal ICA, spatial ICA, PCA, or K-means. So again, it's nice in that it kind of gives us a global summary measure, maybe a little bit more intuitive than getting a whole bunch of numbers out. One example of an interesting metric you can get out is a hub state. So this would be a metastate, really, that if subjects get into this state, they tend to get stuck there. They tend to stay a little bit longer. It's almost like a sticky pattern. And when we looked at the patients, we found that they had significantly more hub states. So they were getting stuck in these states, so to speak. And the degree to which that was occurring was also correlated with their negative symptoms. So again, interesting, and sort of connects it to the symptomatic measures. Okay. Another approach you can use is a time frequency approach, and this is Maziar Yasubi's work, where basically using a complex Morlet wavelet approach. So instead of using fixed windows, we're using wavelets to adapt to the full time frequency information. And one of the advantages of this is that, let me just orient you up here, in terms of how these matrices are colored. Up here, the color tells you the phase. So if it's red, they're in phase. If it's blue, they're anti-phase. And it's essentially continuously colored around the circle. And then the intensity of the color tells you how strong the effect is. So white means a very low signal, and strongly colored means a strong signal. And so one of the advantages is that once we separate these states, we aren't using only the temporal information. We're also getting frequency and phase for each state. So here we can see, similar to what we saw before, we see sort of correlated activity and anti-correlated with default mode here, but we also see the frequency content of this state, which was sort of maxed in about 0.07 hertz, right in the middle of the bold response. This was a lower frequency state. You can see here, around 0.01, 0.07, below 0.07. We also showed, Maziar also showed that you can actually separate out patterns that have similar amplitude patterns but very different frequency spectrum. And you can take this further by expanding the number of basis sets to really try to look for time-varying frequency patterns within the data. And there was evidence in this work that there are 4 different frequency bands within bold fMRI. So fMRI data is pretty low frequency, pretty sluggish. So you might not think there's a lot in there, but there actually is evidence pretty strongly of sort of an ultra low, sort of one that's right in the middle of the bold frequency, more of a broad band, and then more of a sort of really low here. And the real interesting thing about this approach is you can each of these modes was associated with different regions, different components were coming out. But given that we can decompose these different modes, we can also look not only at the connectivity for each of the modes, but we can look at the cross connectivity, the cross frequency coupling. And so, for example, mode 1 and mode 3 here showed a strong sort of effect across default mode across all of the networks. So it appears to be communicating at this cross-frequency coupling. So again, I think there's more information in the bold data than we know yet, and we're still kind of looking. Let me shift a little bit. Another topic that I think demands some further research is looking at, instead of looking at regions or components, you can look at these domains, look at intra-domain information. So this is some work from Jason Nomi and Lucina Uden's group, where they looked at Insula. So they basically used ICA and they decomposed resting fMRI data, and they got 4 Insula related components, and then they looked at how those 4 were connected to each of the other components. So they're getting kind of an Insula fingerprint. The 4 Insula components are indicated in color here. And these 5 different patterns are 5 different states estimated from the data. And there are, asterisks around here that show where there are significant differences between the Insula fingerprints, so to speak. And there are quite a few differences, and they are fairly unique looking. So again, this sort of, again, goes below let's just decompose the data and look for changes in everything. This is saying, well, sort of at this more aggregate level of looking at Insula domains and how those are coupled, what patterns emerge. And you can do this with default mode network as well. And this is some work looking at interaction between subsystems within the default mode network from UPDO, and you can see, over time, some of the changes that are occurring, and we see differences, significant differences in the interaction within just the default mode components between patients and controls. Okay. And you can go further than that. You can actually try to estimate directly from these different domains how they should be clustered or how they should be grouped. Robin Miller has done some work on that, where here we have that sort of static FNC matrix, and then here are domains that were estimated directly from the data. It's essentially trying to taking these domains that are predefined and then looking at one or more clusters within those domains and how those probabilistically interact with the clusters in the other domains. I know there's a lot on this slide, I'm not really going to explain it. Okay, and then I'm going to skip over the fusion stuff for now, and I did want to just talk about one other interesting topic on spatial dynamics. You know, the bulk of work focused on dynamic connectivity now is looking at coupling in time and how that changes. There has been much less work, only a handful of studies looking at spatial regions and how those tend to couple or decouple over time. Ideally, we want to look at both of those, but I think unpacking that a little bit is interesting. Using an independent vector analysis based approach, Simon did some work that showed that you actually do get changes over time. Say here we have a temporal lobe component at different windows of time, just as an example here in a healthy control, and here's a schizophrenia patient, and you can see the schizophrenia patient shows a lot more variability in their spatial pattern over time using this approach than does the healthy control, and you can see that here in the difference. Down here you see a lot more blue and red, where regions are going in and out. Okay, I think this is a very interesting topic, and it also speaks to, you know, how do we define, you know, atlases for the brain. There's been a lot of new studies that have said here are the, you know, 200 or 300 or 400 different regions of the brain. Well, what if this functionally, what if the regions are actually varying over time, and depending on what state you're in, you're actually getting slightly different coupling between the regions. It's a whole other dimension that I think needs to be unpacked. And we can do this with, you know, one sort of straightforward approach is to use this spatial ICA, but instead of looking at the full data set, you can look at only a certain point in time and reconstruct maps from shifting periods of time. This is the default mode network component, and its time course work from Lei Wu, and if we analyze that sort of in the dynamic way, you start to see how these regions kind of shift back and forth in terms of what they're most sort of closely coupled with over time. Again, some very interesting information contained in here. It looks like it's very structured. And I think we need more approaches that can really try to get at the spatial information dynamically. Okay, in the last couple slides, I'll just kind of touch on, there've been a lot of dynamic studies already to date, but there've been a few studies that have been critical of various things, like either the window-based approach, or dynamics in general, saying, well, dynamics, maybe they're just, you know, due to noise or due to, say, sampling variability or something like that. I would argue that we are still a long way from trying to understand what is a good null model for dynamics. You can do some simple things like create surrogate data and you know, do phase shifts to try to create a simulated data set that preserves autocorrelation, etc., and show that we get you know, we get dynamic states when it's consistent, and we get, you know, states that resemble the mean when we don't. You know, it gives us a little bit more confidence, but it doesn't really help unpack the situation. The studies that have been published to date that have tried to use that sort of a null model to reject dynamics or prove dynamics, I think are a bit ill-posed. I think it's a bit of a challenge because you can, it's very easy to simulate a situation in which a static null distribution completely overlaps with a dynamic null distribution. And so, you know, it's really almost impossible to reject the null when we don't really know what that is. So for example, if you think about the brain is dynamic, right? It's constantly updating over time if you have a conscious individual. And the way that the brain the dynamics are reflected in the data is not well understood yet. I mean, we've modeled it, we found, oh, there are changes there, we see differences over time, clear differences over time. But we don't have a good mechanistic understanding of how those changes should be manifested and maybe aren't manifested in order to create a good null for this. So I think this is sort of an open area as well to think about. Even to the point where, you know, we've looked at some of the papers that have been critical of this, and have been very strong in stating that dynamics are just an artifact of the way you're sampling the data. But if you go back and you look at the way some of those studies are simulated, you can generate cases where you get highly dynamic data that you simulate that fails that null test, right? And so I think there are some major issues with some of those simulation studies that are out there that really need to be further studied and further understood. Okay, so in summary, just a few questions that I think are kind of interesting. I mean, this is just some ideas. You can come up with any ideas you want here, but how do you tell if a pair of signals is changing their coupling over time? What's a good way to evaluate that? How do we study that? Should we be focused on changes in connectivity or changes in activity over time? So there's been some work looking at changes over time within one. You take the time course from one component, and you can see changes. For example, Zenning's work looking at changes in alpha over time, or changes in activity over time. So that doesn't look at pairwise coupling. That's just looking at sort of within network connectivity. Most of the work I showed you today was looking at pairwise coupling between component time courses. Those are two different things, and actually they might be it might be informative to look at them jointly in some way, and as well as other things. What about spatial coupling versus temporal coupling, or both? Joint spatial temporal model. What if the signals are a mixture? Maybe there's a more sort of transient effect that comes in and goes out, and maybe there's a more static sort of effect that's sort of a maintenance type thing, right? Are the changes primarily linear? Are there some nonlinear effects that we can estimate robustly? If you're using an ICA-based approach or something like it, what impact does typically we get out these networks, they're data-driven, and then we have to assign labels to them, like default mode or like, frontal lobe or something, right? What impact does that labeling have on your subsequent interpretations? Can we try to automate that labeling somehow? Do the dynamics vary with model order? If we have 100 components versus 10 components, are we capturing at different scales something informative? Can we somehow look at all of that information together? With that, I will close. And I guess what's next? We're gonna do some
I don't know whether
brainstorming ideas.
people have
Somebody wanna do some?
questions. Do you want to stream that, or is that just for us?
I'm okay with it either way. Should we have folks maybe